This is lesson 8.3, properties of planes. We have 3 examples, and before that, just one brief section of notes. The notes are on determining the scalar equation of a plane. So what does it take to actually develop an equation for a plane? We did a bit of this last lesson, but in this case, there is one other thing we can think about. So let's say you're given a vector, and you're told that it is normal to the plane. So it is perpendicular to the plane. That means that there's a plane underneath it or wherever, and this vector is normal to the plane, and it comes also from a point that is on the plane. Okay, that's a necessary piece of information. So basically, in order to develop a equation for the plane, all we need to do is find another vector that is perpendicular to our normal, because that will make it parallel to the plane, and it will come from the same point as our normal vector, because we know our normal vector has its tail on the plane. So if we find another vector like this that is perpendicular to the normal vector and has its tail at the same point as the point of the normal vector, then we can develop a scalar equation for the plane. Because we know it will be perpendicular to the normal, just like our plane is, making it parallel to the plane, and it's actually sitting on the plane because it comes from a point that is on the plane. So I'm going to develop this a little bit further. I'm going to start by just labeling our points. We've got P naught, which is equal to X naught, Y naught, Z naught. And we have the head of this vector. We're going to call this vector P at X, Y, Z. So now we have 2 arbitrary points that are on the plane, and we have a normal vector to the plane. Okay, so what do we know? Well, we know that P naught, the vector P naught P, is parallel to the plane, and it is perpendicular to the normal vector. So let's find that vector. Okay, let's find an equation for that vector from P naught to P. I'm just going to take the coordinates. We've got X naught minus X, Y naught minus Y, Z naught minus Z. Close that off. And now, since this vector is perpendicular to our normal vector, since POP perpendicular to N, what do we know? Well, we know that P naught P dot N equals 0. So let's use that equation, and we'll work this through. So we're going to take our first equation, P naught P, which is XO minus X, Y naught minus Y, Z naught minus Z, dot our normal vector, which is A, B, C. And we know, since they're perpendicular, that's going to equal 0. So now we're going to take the dot product of that, okay? So we're going to take A times, so the x component of each vector, and multiply it together. So A times X naught minus X plus B times Y naught minus Y plus C times Z naught minus Z, and that is equal to 0. And if I distribute this and I reduce this, then I'm going to distribute it all. I end up with A times X naught minus A times X, and then I'm going to have plus B times Y naught minus B times Y. Then I'm going to have C times Z naught minus C times Z. And if I rearrange that, I end up with AX plus BY plus CZ plus, and that, by the way, this has also, looks like it's multiplied both sides by -1 as well, in case you're wondering how I all of a sudden changed the sign. This is negative A times X naught. minus b times y naught minus c times, not a subscript, z naught is set equal to 0. And because this p naught is a point that we know the coordinates for, okay, we know the coordinates for this point, then this value here becomes a known value. So it is simply a constant. There are no variables left. So I can take this piece and I can represent it using just a single letter, d, because it is a known value. So this, ax plus by plus cz plus d equals 0, this is the scalar equation of the plane that has a normal vector ABC. So you can see how we get that. You just are going to end up plugging in A, B, C right there. And you may need to do some work to figure out what D is. But that's a scalar equation of a plane. And we can determine that simply by having the normal vector ABC and knowing where it takes off from at point P naught. So example 1, we are going to develop a scalar equation of a plane when we're given the normal and a point that is on the plane. So here's our normal vector. It is 3, -2, 5. And the point P naught is 1, 2, -3. And we're going to develop a scalar equation for the plane. Develop a scalar equation for the plane. We're going to do 4 different things here. We're going to test if a given vector is parallel to the plane. We're going to test if a given vector is normal to the plane. And then we're going to find another vector that is normal to the plane. So here we go. Step 1. We know we have the normal. We know we have a point on the plane. So what's the next thing that we can do? We're going to find, or we're going to allow there to be another point on the plane, and that's going to give us a vector that is parallel to the plane from this same point, therefore on the plane. So here's what we're going to do. We're going to let P be the point x, y, z on the plane. Let P be a point on the plane. All right. That's going to give us another vector. We're going to get P naught P, okay? And that's going to be x minus 1, y minus 2, z minus -3, which is z plus 3. Now, if this is a vector on the plane, it must be perpendicular to, or orthogonal to, our normal vector, okay? Which means that the dot product will be 0. So P naught P dot n equals 0. Let's fill in our vectors. X minus 1, y minus 2, z plus 3, dot 3, -2, 5 equals 0. Take the dot product of this, we end up with 3 times x minus 1 minus 2 times y minus 2 plus 5 times z plus 3, set equal to 0. Keep on expanding this and simplifying. I get 3x minus 3 minus 2y plus 4 plus 5z plus 15 equals 0. And I'm going to write this in standard form, or scalar form, scalar equation. I'm going to take all of my constants and group them together at the end. So I've got 3x minus 2y plus 5z, and it's looking like 15 plus 1 is plus 16 equals 0. And there we have a scalar equation for the plane. Now, this was method 1. Method 1, using the dot product. But, and you may have thought of this earlier, There's an easier way to do this, or at least a shorter way to do this. And we're going to call that method 2. I'm going to do it over here. And that's going to be using the scalar equation itself. So ax plus by plus cz plus d equals 0. If that's the standard form that we're going for, we know something else about the components of the normal vector. The components of the normal vector are the coefficients of x, y, and z in the scalar equation for the plane. We learned that last lesson. So that tells us that, or maybe I can say since, the components of n are the coefficients of the scalar equation, I can simply write 3x minus 2y plus 5z plus d equals 0. Now, we're still missing d. So you can see how it's already correct. The first 3 coefficients are known just by looking at the normal vector. But we still need a constant value in order to finish off this, this equation. So what else do we know? Well, we know that p naught, 1, 2, negative 3, is on the plane. That means that the coordinates 1, 2, negative 3 satisfy this equation. So you can see how I'm going to be able to fill in x equals 1, y equals 2, z equals 3, and now the only variable left is d. I'll be able to solve this for d. So we've got 3 minus 4 minus 15 plus d equals 0. This is negative 15 minus 1 more is negative 16. Add 16 to both sides, I get d equals 16. Therefore, 3x minus 2y plus 5z plus 16 equals 0. Now this side looked a bit longer, and it maybe even took us longer, but that's just because I was explaining it as we went and writing little notes. You would just write this, sub in the points that you know that will satisfy the equation in order to solve for your last missing constant there, and then rewrite the equation in scalar form. In section B, example 1b, we are asked to determine whether or not a vector is parallel to the plane. So we're given vector A is 4, 1, negative 2, and asked, is it parallel? Well, in order for it to be parallel to the plane, it needs to be normal to the normal vector. It needs to be perpendicular to the normal vector. So all we really need to do is find the dot product of a dot n. A dot n would have to equal 0. Okay, so let's figure that out. Here's the vector a, 4, 1, negative 2, dot the vector n, 3, negative 2, 5. And taking the dot product, we end up with 4 times 3 plus 1 times negative 2 plus negative 2 times 5. 12 minus 2 minus 10, and that is 0. Therefore, A is parallel to the plane. In C, we need to determine, we're given vector B, we need to determine if vector B, 15, negative 10, 25, is normal to the plane. Now we already have a vector that's normal to the plane. So if vector n is normal to the plane, in order for vector b to be normal to the plane, it needs to be parallel to vector n. Now in 3 space, that means, so for instance, in 2 space, that would mean it has the same rise over run, but it could be any multiple of the rise over run. It has the same slope, right? So in 3 space, the direction vector, the direction that this is going in needs to be the same as the direction that's going in, which means that b needs to be some scalar multiple of n. The x coordinate, the y coordinates, and the z components need to each be multiplied by the same constant and arrive at the corresponding value, if that makes any sense. So what we're saying is that there must be k such that b is equal to k times n, okay? B needs to be some scalar multiple of n. That's not going to change the direction of n. That's going to make b parallel to n, even though the vector itself might look very different, okay? So let's rewrite this using our vector notation here. We've got 15, negative 10, 25 needs to be equal to k times 3, negative 2, 5. So let's test it out for our x component, our y component, and our z component. X, y, z. So 15 equals k times 3, or 3k. Divide both sides by 3, I get k equals 5. The y component, negative 10 is equal to negative 2k. Divide both sides by negative 2, I get k equals 5. It's looking good so far. Z component, 25 is equal to 5k. Divide both sides by 5, k equals 5. All right, so since there is a scalar multiple, since the vector b is a scalar multiple of the vector n, means it's heading the same direction, regardless of where it is, it's heading the same direction. It is then normal to the plane. Therefore, b is normal to the plane. And D wants us to find more vectors normal to the plane. Normal to the plane. Well, there's a couple ways you can think about this. If a vector is normal to the plane, it's going to be some scalar multiple of the normal vector that we started with, which I have right here. Or it's going to be normal to any of the vectors that lie on the plane, or any of the vectors that lie parallel to the plane. So in the first section, we found out that A was parallel to the plane. Well, if I found a vector that was normal to A, it would also then be normal to the plane. Okay, so there's a couple of different ways to think about this. We're just going to pick any scalar multiple of n. Any scalar multiple of n. So it doesn't really matter. Let's go 3n. 3n would equal 3 times 3, negative 2, 5. That would be the vector 9, negative 6, 15. All right, there's one example, and you could build other vectors the same way. In example 2, we're going to develop an equation, and we're only going to be given points on a plane. In order to define a unique plane, we need 3 non-collinear points. So that's what they give us. That's going to be given. We're given the point A at negative 3, negative 1, negative 2. B at 4, 6, 2. And C at 5, negative 4, 1. Negative 4, 1. Okay, now because these points are on the plane, by the way, what do we need in order to develop an equation? Well, we need a normal vector, and the relationship between that normal vector is going to give us the first 3 coefficients of the scalar equation, and then we're going to use one of the points up here in order to find d in ax plus by plus cz plus d equals 0. Yes? So the first thing that we're going to do is actually find a couple of vectors that are on the plane. So if the plane contains the point A, B, and C, then the vector that gets us from A to B, or the vector that gets us from A to C, or the vector that gets us from B to C, all of those vectors are on the plane. Okay, so first let's find vectors on the plane. Vectors on the plane. And we're going to find two of them. We're going to get AB. In order to find AB, I would be going 4 minus negative 3, which is 7, 6 minus negative 1, which is 7, and 2 minus negative 2, which is 4. So the vector AB is on the plane. Let's get AC. AC, I've got 5 minus negative 3, that's 8. Negative 4 minus negative 1, that's negative 4 plus 1, that's negative 3. And 1 minus negative 2, that's positive 3. Now that I have two vectors on the plane, remember, now we're applying a lot of our knowledge, okay? I'm going to take the cross product of these two vectors. Remember, the cross product of two vectors will create a third vector that is perpendicular to both of your original vectors, okay? Let me write that before we do it. The cross product AB cross AC is a vector perpendicular or orthogonal to both AB and AC. So here we go. Cross product AB cross AC. So we have 7, 7, 4 cross 8, negative 3, 3. Now remember how to do the cross product. We're going to have, I can draw the picture. Why don't I draw the picture off to the side? That's what our textbook does, and that's helpful. So we've got I, J, K, I, J, K. And then we have one of our vectors is 7, 7, 4, 7, 7, 4. Our other vector, AC, is 8, negative 3, 3, 8, negative 3, 3. And now if we want to find the I component of our cross product, we're going to be tracing down 7 times 3, and then we're going to be subtracting, by tracing back up to the I, we're going to be subtracting negative 3 times 4. Okay, so that's our first part. I'm going to write that down, and actually I'm going to end up running out of space, so I'm just going to bring this over here. We've got 7 times 3 minus negative 3 times 4. Okay, that's our x component. Now we're going to be looking for our multiples of our j unit vector j. That's the unit vector in the y direction. So we're going to be multiplying down 4 times 8. And then we're going to subtract 7 times 3, or 3 times 7. Okay, so we've got 4 times 8 minus 3 times 7. And now our multiples of our unit vector in the z direction, we've got 7 times negative 3 minus 8 times 7. So we've got 7 times negative 3 minus 8 times 7. Let me just cap all my markers here for a second. Good, good. And now I simplify. 21 plus 12 is 33. 32 minus 21 is 11. and negative 21 minus 56 is negative 77. So even if I can't picture this in my head, I know that this vector that we've created is the cross product of our two original vectors that are on the plane. Therefore, this is perpendicular or normal to the plane. So now we have a normal vector, or a vector that is normal to the plane. Okay, so we have an n that equals, maybe I'll just write this here, n equals. Now, we also know that any scalar multiple of this vector will also serve us as a normal vector, because any scalar multiple of this vector is parallel to our normal, making it another vector that is normal to the plane. So can you think of something I can do to these numbers, 33, 11, negative 77, in order to create a new normal vector that is easier to work with? Oh, you're so smart. 3, 1, negative 7 is just a more convenient vector to work with. It's parallel to this vector, therefore it is also normal to the plane that we are working on. Well, now that I have a normal vector, I can just sub those components in as the coefficients of my scalar equation for the plane. So that gives us 3x plus y minus 7z plus d equals 0. For our last point is to try to figure out what d is. I can sub in any of my 3 points that fall on the plane. We'll take point A. So I've got 3 times negative 3 plus negative 1 minus 7 times negative 2 plus d equals 0. This is negative 9 minus 1 plus 14 plus d equals 0. We've got 14, take away 10, that's 4. Subtract 4 from both sides, it's d equals negative 4. Therefore, the scalar equation that we have for this plane, given starting with 3 points, is 3x plus y minus 7z minus 4 equals 0. That's the scalar equation for the plane. Okay, in example 3, we're going to write equations for a plane again, but this time we're not going to be given 3 non-collinear points. We're not going to be given a normal. Instead, we're just going to be given some general information. We're going to have to use our knowledge of the properties of planes in order to determine an equation for the plane. It's going to involve things like finding the normal or using a point on the plane, those kinds of things. So in A, we're told that we have a plane that is parallel to the xz plane through the point negative 7, positive 8, positive 9. All right, well, the xz plane, that has a normal vector. Let's think about normal vectors, right? Well, if we're thinking about our xz plane, and maybe I can just draw something out for us here. So we've got z, x, and y. This is negative y, this is negative z, this is negative x. So our xz plane is then this plane, and we actually know a vector or a line, or however you want to think about it, that is always must be perpendicular to both the x and the z axis, and that is going to be the y-axis, right? So one possible normal to this plane would be the unit vector along the y-axis, and any multiple of it, right? You can come forward from this or backward from this. You can do the same thing over here or over there. Whatever it is, some multiple of this unit vector along the y-axis is going to be normal to the plane, the xy plane. So our normal vector here is j, and j has the position vector 0, 1, 0. So a scalar equation for this plane, it gets real simple, right? Let's just put this into a scalar equation. We've got 0x plus 1y plus 0z plus d equals 0. This is 0. Y plus d equals 0. And we know that the plane contains this point. So that means -7, 8, 9 satisfy the equation. All we need is the value for y in order to determine d. So I'm going to sub in x, y, z. I'm going to sub in 8 for y, which tells me that d equals -8, which tells us that the scalar equation is y minus 8 equals 0. That's the equation of the plane that is parallel to the xz plane and goes through this point. So how you could think about that is it's basically if you had a plane on the xz plane and then you're going to move it forward 8 units along in the y direction. And I think I can fit B here as well. In B, it's going to contain the line x, y, z equals 1, 2, 4 plus some multiple of our direction vector for 1, 11. And it's going to be perpendicular to this line. X, y, z is equal to 4, 15, 8. That's a position vector times some multiple of our direction vector, 2, 3, -1. Okay, so it contains this given line, which, by the way, automatically gives us a point and a line on the plane. And because this line, this vector, this line is perpendicular to this line, we know that this second line can serve as a normal to the curve, okay? Its direction vector, its direction portion, okay? Okay, since, I'm not going to rewrite it, since equation 2 is perpendicular to equation 1, then its direction vector can serve as the normal vector to the plane. Okay, so we're given a normal vector then is 2, 3, -1. Therefore, our scalar equation has the form 2x plus 3y minus 1z plus d equals 0. And then from equation 1, because we're given a point on the plane, we can sub that in to solve for d. So we've got 2 times 1 plus 3 times 2 minus 4 plus d equals 0. This is 2 plus 6 minus 4 plus d equals 0. 8 minus 4 is 4. Subtract 4 from both sides. D equals -4. Therefore, our scalar equation is 2x plus 3y minus z minus 4 equals 0. So that's the scalar equation for the plane in example 3b. And that's it for this lesson. Shortest lesson of the unit by far. We're thankful for that. And your practice problems can be found on page 459. And you're responsible for knowing how to do numbers 1 through 20. Enjoy.